Hi friends, today we are starting to watch this video, not in a single session, we'll do it I think in 3. It's interesting, it's about, she is explaining or summarizing a book which is called AI Engineering by Chip Eugene, and this is a book I'm actually reading now, but so I think it will be useful to hear from her a summary of the whole thing, to have like an overview about it. And then if you want to get into it, you can DFS into it, actually reading it, you know. So let's go. I will stop the video when I think that I can say something that might be interesting. So I hope you enjoy it.
Hey everyone, today we're diving into the book AI Engineering by Chip Wynn. 800 pages of really great content about this in-demand field that's offering salaries of $300,000 or more. In this video, I'm summarizing everything from the book to help you get a high-level overview of the field. We'll talk about foundation models, prompt engineering, RAG, fine-tuning, agents, how to build a system, improving inference, and more. I also want to mention, this is a super high-level overview of a very detailed technical book. Don't expect to learn all the details just from watching.
So this AI engineering thing is like it's a new term. Actually, the book explains how the term started. For me, it's like the new full stack. It's like people creating products over LLMs and similar technology, knowing how to fine-tune them or which kind of better AI API to use and how to do something useful over it. So I think that's more or less what AI engineering is about, you know. So it's like creating applications over LLMs and similar. And the foundation and models is what the raw LLM is about, like for instance, Llama or those kind of things, or ChatGPT.
Video. I really recommend using this as a way to get an overview of what the field looks like and use it as a jumping off point for your own research and exploration. So what exactly is AI engineering and how is it different from traditional machine learning? Let's break it down. AI engineering has exploded recently for two simple reasons. AI models have gotten dramatically better at solving real problems, while the barrier to building with them has gotten much lower. This perfect storm has created one of the fastest growing engineering disciplines today. At its core, AI engineering is about building applications on top of foundation models, those massive AI systems trained by companies like OpenAI or Google. Unlike traditional machine learning engineers who build models from scratch, AI engineers leverage existing ones, focusing less on training and more on adaptation. These foundation models work through a process called self-supervision. Instead of requiring humans to painstakingly label data, these models can learn by predicting parts of their input data. This breakthrough solved the data labeling bottleneck that held back AI for years.
So what the book talks about here is that in machine learning, you are supposed to have a huge effort in order to label the data, and then I don't know, for instance, you need to create a model that is going to be able to know if something is a dog or a cat. So you need to have a lot of photos labeled with dog or cat. Whereas this kind of LLMs, you have a huge kind of data, which is, for instance, internet being crawled. And what you are going to do is just use that data. Perhaps you are improving the quality of it. And it's already, the labels is like they are already intrinsic into the data. You don't really need to label all those terabytes of text. It's like the text is already has already the label with the relation of how the words appear among themselves, right? So it's different. It's in that kind of things. That's what they call that it's self-supervised.
Years. As these models scaled up with more data and computing power, they evolved from simple language models to what we now call large language models, or LLMs. And they didn't stop there. They've expanded to handle multiple types of data, including images and video, often becoming large multimodal models. Nowadays, we're seeing foundation models power everything from coding assistants like GitHub Copilot to image generation tools, writing aids, customer support bots, and sophisticated data analysis systems. Now that we've covered what AI engineering is, let's dig deeper into foundation models themselves, how they're trained, how they work, and why understanding their architecture matters for AI engineers. Foundation models at their core can only know what they've been trained on. This might seem obvious, but it has profound implications. If a model hasn't seen examples of a specific language or concept during training, it simply won't have that knowledge. Most large foundation models are trained on web-crawled data, which brings some inherent problems. This data often contains clickbait, misinformation, toxic content, and fake news. To combat this, teams use various filtering techniques. For instance, OpenAI only used Reddit links with at least 3 upvotes when training.
So it's like OpenAI downloaded the whole internet and probably everything they found in an archive or any torrent with data, books, and everything. But they did an effort in order to improve the data. And she's explaining an example that appears in the book, which is that instead of crawling Reddit in depth, you just get 3 levels of answers, like the top three answers, and you do the same with the Stack Overflow. You only get the right answer and perhaps the 2 most voted. And so you do those kind of strategies in order to have a better version of the internet that you need to fit in order to create the model.
GPT-2. The language distribution in training data is also heavily skewed. About half of all crawled data is in English, which means languages with millions of speakers are often underrepresented. This is why specialized models for specific languages and domains are becoming increasingly important. Also, the distribution of domains in one of the main training datasets leans heavily towards business, tech, news, and art. In terms of model architecture, most foundation models use transformer architectures based on the attention mechanism. But to understand why transformers were such a breakthrough, we need to look at what came before. Transformers were invented to solve the problems of sequence-to-sequence models, which used recurrent neural networks for tasks like...
In this part, she's explaining what the transformer is and what attention is, and starting comparing it with the previous systems. So in this part of the book, it's quite easy to lose your attention while you try to understand what attention is, but it's not really a big deal, because what you want to do is understand that naively or have a bit of an idea, but then move forward and see the other more practical things that you actually need as an AI engineer. I probably people are working with these kind of things and making products without even understanding in depth what attention is.
Like translation. These had 2 main components, an encoder that processes inputs and a decoder that generates outputs. Both worked sequentially.
So this is the old architecture, you know, 1 to minute, you know, before transformers and attention mechanism.
Token by token. The problem is that the decoder only has access to a compressed representation of the entire input. Imagine trying to answer detailed questions about a book when all you have is a brief summary. Also, input processing and output generation are done sequentially, so it's slow for long sequence. Transformers solved this with the attention mechanism, which allows the model to weigh the importance of different input tokens when generating each output token. It's like being able to reference any page in the book while answering questions. Plus, transformers can process input tokens in parallel, making them much faster. During inference, transformers work in 2 steps. First, prefill. Process all the input tokens in parallel to create the intermediate state. And second, decode. Generate 1 output token at a time. The attention mechanism uses 3 types of vectors. First, query vectors. These represent what...
I'm speeding up this part because if you want to see it slower, just go to the original video that I'll put the link, but I'm not really super interested in paying a lot of attention to the depth of this part. So let's go to...
Hey everyone, today we're diving into the book AI Engineering by Chip Wynn, optimizing the foundation model to generate responses that match 60 billion transmitter capacity. Next, models use transformers with millions of speakers code, generate 1 output token at a time. The attention mechanism uses 3 types of vectors. First, query vectors. These represent what information the model is looking for. Next, key vectors, like indices of previous tokens. And finally, value vectors, the actual content of the previous tokens. The model computes how much attention to give each input token by comparing the Q and K vector. A high similarity score means that the token's content, V, will heavily influence the output. This is why longer context windows are computationally expensive. More tokens mean more K and V vectors to compute and store. Attention is almost always multi-headed, allowing the model to focus on different groups of tokens simultaneously. In Llama 2.7b, there are 32 attention heads, for example. A complete transformer consists of multiple transformer blocks, each containing an attention module and a neural network module. The number of blocks is often called the number of layers. Before and after each block, there's an embedding module that converts tokens and their positions into vectors, and finally an unembedding layer that maps output vectors to token probabilities. So that's a super high look at this. I would really recommend either reading the book or check out StatQuest for an awesome overview of transformers and the attention mechanism. I'll link that in the description. That's really how I learned. While transformers dominate, they're not the only architecture.
That's really how you learn it, yeah.
Models like RWKV, which combines RNN-based approaches with parallelization capabilities, are gaining traction for certain applications. In general, larger models with more parameters have greater capacity to learn and perform better. The number of parameters helps us estimate the compute resources needed for training and inference as well. However, note that parameter count can be misleading with sparse models, so those with many zeros, which can be more efficient. A large sparse model might require less compute than a smaller dense one. When designing models, compute is often the limiting factor. The chinchilla scaling law helps calculate the
Now that she's talking about the chinchilla law, which is like a theorem or a way to how much is going to cost you training a model.
optimal model size and data size for a given compute budget. It suggests that the number of training tokens should be about 20 times the model size. So a 3 billion parameter model needs about 60 billion training tokens. While the cost for achieving the same model performance is decreasing over time, the cost for improvements remains high. Going from a 3% to a 2% error rate might require an order of magnitude more data, compute, or energy. But even small performance improvements can make a huge difference for downstream applications. As we keep scaling models, we're approaching two significant bottlenecks. First, training data. There's concern we'll run.
But here she's still talking about things that you are not going to do unless you try something like the nano chat like Carpathy, that you can train like a GPT to like even less LLM, paying 100 euros or dollars for each 100 GPUs. You can try that and have like a quite dummy LLM, but usually I don't know, like the AI engineering thing is not about creating your own models, more like using them and knowing how to fine-tuning them or integrating them with the stuff. So this is still, I don't know, not so interesting. So we are going on with the fast speed.
Run out of high-quality internet data in the next few years, forcing models to train on AI-generated content, potentially causing performance degradation, or requiring access to proprietary data like copyrighted books and medical records. Second, electricity. Data centers already consume 1 to 2% of global electricity, limiting how much larger they can grow without significant energy breakthroughs. Pre-trained foundation models face two main issues. They're optimized for text completion, not conversation, and their outputs can be factually incorrect or ethically problematic. Post-training aims to address these issues through two main steps. First, supervised fine-tuning. Supervised fine-tuning optimizes the model for conversations instead of completion. This requires high-quality instruction data, showing the kinds of requests the model should handle and how it should respond. It's essentially teaching the model what good responses look like. Second, preference fine-tuning.
Here what the book says is that when you train the model, or the behavior, the default behavior is not what you are usually used in ChatGPT and others. You need to actually post-train the model with a set of question and answers so that it gets the way of the flavor of answering you the way you expect. That I guess that's why it says things like you're absolutely right, and it has like kind of a personality that sometimes you can feel. It's not trained, or the training itself of the LLM just make it behave like a pure autocomplete, like the keyboard one. If you want it to behave like a bot or something, you need to.
Preference fine-tuning aligns the model with human values using reinforcement learning, often called reinforcement learning from human feedback. This involves training a reward model that scores outputs based on human preferences and optimizing the foundation model to generate responses that maximize these scores. While reinforcement learning from human feedback has been the standard approach, newer
I saw this in the book. It's like a Kira blog.
methods like direct preference optimization, DPO, are gaining traction. Some companies even skip the
Like this Akira thing, if you watch it, is like it says like the model once trained is like horrible or it's really ugly, and then you need to do the little thing. You need to do the reinforcement learning thing, you know, the cherry on top, in order to make it look good, you know. That you can see that there was like a huge effort from OpenAI, so that when we tested the GPT-3, it was not a raw model of autocomplete. It has like a great experience on top.
like direct preference optimization, DPO, are gaining traction. Some companies even skip the reinforcement learning step entirely, instead generating multiple outputs and selecting those with high reward model scores. This is a strategy called best of N. Foundation models don't just produce a single definitive answer. They generate probabilities for possible outputs. How we sample from these probabilities.
Now she's explaining the part of the book that talks about attention, not really attention, about temperature and sampling and the randomness that you need in order to have more creative responses.
These dramatically affects the model's responses. The simplest approach is greedy sampling, always picking the highest probability token, but this leads to repetitive, predictable text. To introduce creativity, we use sampling techniques. Temperature controls how confident the model is in its predictions. Higher temperature values, like 0.7 to 1, make outputs more creative but potentially less accurate, while lower temperatures, close to 0, make outputs more deterministic and focused. Top K sampling restricts the model to choosing from only the K most likely next token.
For instance, you can pick the 0 temperature. I've seen that in some integrations that try to mimic like a search engine, and it's supposed to use those tokens that have more probability to be together, if you want to talk like that. But you are not having a sense of creativity, and you might also have like answers that are repeating themselves even in the same reply. So usually you want something in the middle and more near to the 1 than to the 0. I think it's a common practice. because it's not really 100% related to the hallucination. That's like a bigger problem. You cannot really avoid hallucination just putting a 0 into the temperature. That's like a different problem.
Typically between 50 and 500, depending on how diverse you want the response. Top P sampling selects the smallest set of tokens whose cumulative probability exceeds a threshold P. A value of 0.9 means the model will only consider tokens that together make up 90% of the probability mass. This probabilistic nature explains many of the behaviors we see in foundation models, like inconsistency with minor input changes and hallucinations where models confidently state incorrect information. Now that we understand foundation models a little more,
yes, but later the book explained that hallucination is a bit more complex, because at this point you might think, okay, I put 0 temperature and I'm fine and there are no hallucinations. That would be great, but it's not the case.
let's talk about one of the most crucial yet underappreciated aspects of AI engineering, evaluation. For some applications, figuring out...
Now she's starting to talk about the part of the book when, well, given that you have trained a model or you have a model, you want to evaluate the quality of it, and it's like an open thing, because it's not something easy. There are a lot of benchmarks, there are a lot of, you can compare even an LLM compared to another one, but what are you going to compare? A set of question and answers, and you might have something like trying to evaluate code. Perhaps you can try to run it, and if it runs, it might be okay. So there are different strategies depending on the output you are talking about, because if it's something, it's like art, for instance, you want to ask a poem to the LLM, how are you going to see if it's good quality or not? Perhaps it's something subjective, or you can check the metrics of the poem and see if the words have like the, if they rhyme, you call it. And if it's code, perhaps there are a lot of good code LLMs, because it's easier. Or at least you can check with a linter if it's okay, and where it runs, and even if it is able to run certain tests. But in another kind of things, it might be more difficult.
Evaluation can consume the majority of your development effort. It's how you mitigate risks, uncover opportunities, and gain visibility into where your system is failing. Evaluating AI systems is significantly harder than traditional ML models for several reasons. First, the problems these models solve are often inherently complex. Evaluating a mathematical proof or the quality of a summary requires deep expertise. You might need to read an entire book just to judge if a summary captures the key points correctly. Second, tasks are typically open-ended with many possible correct responses. Unlike classification, where there's one right answer, a question like, write me a poem about resilience, has countless valid responses. Third, foundation models are black boxes. You can only evaluate them by observing their outputs, not by understanding their internal workings. Fourth, publicly available evaluation benchmarks quickly become saturated, which is when the model achieves perfect scores. What was a challenging test yesterday becomes an easy exercise today. And finally, for general purpose models, you need to evaluate not just known tasks, but discover new capabilities that might extend beyond human abilities. All of this is made worse by a general underinvestment in evaluation compared to model development. So let's start with some fundamental metrics used to evaluate language models during training. Most autoregressive language models are trained using cross-entropy, or its relative, perplexity. These metrics essentially measure how well the model predicts the next token in a sequence. Entropy measures how much information, on average, a token carries.
This is explained into concepts, entropy and perplexity. Well, it's good for culture, for AI culture. It was more interesting the previous thing that she was talking about black boxing, the fact that the LLMs are black box. That once you have an output and you see like, okay, the quality is bad, can I trace back to why the model was having that behavior? That's quite of a problem, and you cannot, I don't know. That's why the black box thing is interesting. It's very different to what we are used to in traditional software engineering, where you could go into the code and to trace back to see that there is like an if or switch that has a bad logic. With this kind of things, it doesn't work that way. Sometimes it's like, on average, it's okay, and then like a 101% or something like that is not okay, but you go with it because, well, the discipline is now at that level. I don't know.
The higher the entropy, the more information dense each token is, and the more unpredictable the language. If you can perfectly predict what I'll say next, what I say carries no new information. Language models learn the distribution of their training data. The better a model learns this distribution, the better it becomes at predicting what comes next, resulting in lower cross-entropy. A perfectly trained model would achieve cross-entropy equal to the entropy of the training data itself, and the KL divergence between the two will be 0. Perplexity is simply the exponential of cross-entropy. It measures the amount of uncertainty a model has when predicting the next.
Perplexity is how I am right now. No, it's like a formula, when you see or read the book, they explain it carefully, and you see it's basically a formula, not really.
Higher perplexity means that there are more possible options the model is considering. What counts as good perplexity depends entirely on the data. More structured data has lower expected perplexity because it's more predictable. The larger the vocabulary, the higher the perplexity because there are more possible options. And the longer the context length, the lower the perplexity tends to be. While perplexity is useful for guiding training and serves as a proxy for a model's general capabilities, it becomes less reliable for models that have undergone significant post-training with SFT or RLHF. As models get better at completing tasks, they might actually get worse at predicting the next token in a statistical sense. Perplexity can also be used to detect if a text was in a model's training data, because it would be unusually good at predicting those tokens, and to identify nonsensical text, which would have abnormally high perplexity. For some tasks, we can perform exact evaluation, where there's no ambiguity about the correct answer, like multiple choice question. This is in contrast to subjective evaluation, like grading an essay. The gold standard here is functional correctness, evaluating whether the system performs its intended functionality. For example, if I ask a model to book a restaurant reservation, did it make the correct reservation? This is the ultimate metric for any application, though it's not always clear how to measure it. In coding tasks, functional correctness translates to execution accuracy. Does the code run and produce the expected output? For gaming bots, we can measure objective performance metrics like win rates. When reference data is available, we can evaluate outputs by comparing their similarity to this ground truth. This approach is bottlenecked by how much and how fast reference data can be generated, either by humans or AI. There are three main ways to compare outputs to references. First, exact match, a binary measure that works for simple questions with definitive answers, like who was the first woman to win the Nobel Prize? Second, lexical similarity, a continuous measure of how much the tokens overlap between the output and reference. This can use techniques like edit distance, how many changes are needed to transform one text into another, or n-gram overlap metrics like blue and rouge. The drawback is that you need a comprehensive set of reference responses, and the references themselves can be wrong. Plus, higher lexical similarity doesn't necessarily mean a better response. There are many ways to express the same idea. Third, semantic similarity. This is a continuous measure of whether two texts have the same meaning, regardless of the specific words used. This is typically implemented by comparing text embeddings using metrics like cosine similarity. The advantage is that it doesn't require references, but it does depend on the quality of the underlying embedding algorithm. One of the most powerful and common methods for evaluating AI models in production is using another AI model as a judge. These AI judges are fast, easy to use, and relatively cheap compared to human evaluators. They can work without reference data and can judge attributes like correct.
This is similar to Minority Report, I think it was. Let me check. Do you remember this? That they were like, I think there were three girls. Yeah, there were three girls, kind of AI, you know. Were not really AI, they were like humans, weird humans, but I would just remember this. That they had a response and they need to agree in order to know that the answer had quality. So this is kind of that, you know. Okay, let's go on. I'm slowing it to normal speed because this is starting to be a bit more practical now. And practicality is good. Perplexity is not so much.
Toxicity, hallucinations, and more. Studies have shown that AI judges can correlate strongly with human evaluators, sometimes showing higher agreement than between different human judges. They can also explain their decisions, which helps with transparency. You can use AI judges to score outputs, compare outputs to references, or pick the best of two responses. Since language models are generally better with text than numbers, AI judges tend to perform better with classification tasks than numerical scoring. When creating prompts for AI judges, you need to include the evaluation task, criteria, and scoring system. Few-shot examples generally work better than zero-shot, which we'll talk about later in the prompt engineering section, though longer prompts do increase costs. Interestingly, you don't always need your strongest model as the judge. Specialized, smaller models can often perform evaluation tasks effectively, which helps reduce costs. However, of course, AI judges have limitations. Like all AI applications, they're probabilistic. The same judge given the same input can produce different scores if prompted differently or simply run twice. This makes evaluation results harder to reproduce.
That's a behavior that the LLMs have in general, that you ask for something, for a question, and you have a result. It's okay now, but if you ask again, perhaps the quality is lower. That's what is a bit of frustration sometimes with these systems. So if you put a judge in order to judge your AI, it happens the same. Now it might say that your quality is okay, but then not. So I don't know. I mean, actually, when I read that in the book, is somebody actually using this thing of the AI judge? Perhaps if you want, I can imagine that you have just trained ChatGPT 5 and you want to test it, and you can run pipelines that are running ChatGPT 4, checking whether the outputs of ChatGPT 5 are okay or something like that, and see a report of that.
Or trust. Additionally, metrics aren't standardized across different systems. One system's definition of faithfulness might differ from another's. Models also exhibit biases. They might prefer responses from the same model. This is called self-bias. Favor the first answer in a comparison. This is position bias. or prefer lengthier answers, verbosity bias. You can mitigate these biases through techniques like randomizing the order of responses, but this also increases costs. Now that we understand evaluation, let's tackle one of the most crucial decisions in AI engineering: model selection. With the increasing number of readily available foundation models, the challenge isn't developing models, but selecting the right one for your application. During application development, you'll go through model selection multiple times as you progress through different adaptation techniques. For instance, when doing prompt engineering, you might start with the strongest model to evaluate feasibility, then work backwards to see if smaller models would suffice. If you decide to fine-tune, you might start with a small model to test your code before moving to a larger one. The selection process typically involves two key steps. First, finding the best achievable performance on the task, and then second, mapping models along a cost-performance axis and choosing the model that gives the best performance for your budget. Your criteria for evaluating.
This is a big thing now when you try to build applications over LLMs, and it's the cost. If they weren't so expensive, you would use the top one. You could use GPT-5 Pro or something like that and be fine. But at the end of the day, perhaps it's okay with just GPT 3.5 and you're fine. I don't know.
The model can be organized into 4 buckets. First, domain-specific capabilities. How well does the model understand your specific domain? For example, if you're summarizing legal documents, how well does it understand legal terminology? Second, general capabilities. How coherent, faithful, or factually consistent are the outputs? Third, instruction following capabilities. Does the model follow the format and structure you requested? And fourth, cost and latency. How expensive is the model to run, and how quickly does it respond? Sometimes, rather than evaluating absolute quality, you just need to determine which model is best for your use case. This can be done through point-wise evaluation, so you score each model independently, or comparative evaluation, where you directly compare output. When evaluating models, you also need to differentiate between hard attributes and soft attributes. Hard attributes are impossible or impractical to change. These include license restrictions, training data composition, model size, privacy requirements, and the level of control you need. These are often determined by the model providers or your own internal policies, and they can significantly limit your pool of options. Soft attributes, on the other hand, can be improved through adaptation techniques like prompt engineering or fine-tuning. These include things like accuracy, toxicity, and factual consistency. A high-level workflow for model selection looks like this. Filter out models whose hard attributes don't work for you. Then use publicly available information like benchmark performance to narrow down to the most promising candidates. Third, run your own experiments to find the best model given all of your objectives. Fourth, continually monitor your chosen model in production to detect failures and collect feedback. Most companies won't build foundation models from scratch, so another question is whether to use commercial model APIs or host an open source model yourself. Let's clarify some terminology first. Originally, open source meant any model you could download and use, but some argue that a model should only be considered truly open source if its training data is also publicly available. This allows for more flexible usage like retraining from scratch with modification. Models with open weights but closed training data are sometimes called open weight models, while those with both open weights and open data are open models. So most so-called open source models are actually just open weight. These models also come with different licenses that may restrict commercial use or limit how you can use the model's outputs for training other models. For a model to be accessible to.
So here they explain the difference between open models and open weights. And typically you don't have access to the data that was used to train it, so that it's just open weights. And the problem that it says that you cannot really train the model if you don't have the data, so it's not open data. In practice it doesn't matter because you need so many GPU hours to train it yourself that it doesn't matter.
To users, a machine needs to host and run it. The service that hosts the model and handles queries is often called the inference service, while the interface the users interact with is the model API. After creating a model,
Yeah, so performing inference, I think it's the first time she talks about the term, is just asking something to the model and having the response back. That's inference. The process of searching of creating a response for you with those tokens, or creating those tokens.
Developers can choose to open source it, make it accessible via an API, or both. Typically, model providers open source their weaker models and keep their best ones behind paywalls. Whether to host a model yourself.
I think OpenAI is a good example of that, right? That they released the GPT OSS, which is pretty good, actually. I think I have both installed, DeepSeek and that one. Perhaps that one is better than DeepSeek, I don't know. It's difficult to. But then if you actually want something that works right, you need to go with GPT-5. Which is the one which you need to pay for in order to have the real quality.
or use a model API depends on several factors. First, data privacy. If your company has strict data privacy policies that prevent sending data outside the organization, externally hosted model APIs are not an option. There's also the risk that API providers might use your data to train their models. Next, data lineage and copyright. Most models aren't transparent about their training data, and intellectual property laws around AI are still evolving. It's unclear whether using a model trained on copyrighted data could create legal issues for your.
That's an open legal thing, that there are people that say that at some point the laws will make sure that only those models whose data had the granted copyright are legal, but that's difficult. That would kill almost every model right now. I mean, it's difficult to have good large enough training data if you need to care about all the copyright. That's something that only those which are the owners of all that copyright could do, you know. For instance, I think I read that an archive, which is a place where there are a lot of EPUBs, was used by Facebook in order to train Llama. That's one example, you know.
Product. Next, performance. The gap between open-sourced and proprietary models is closing, but the strongest models will likely remain proprietary. Commercial APIs often provide additional capabilities out of the box, like scalability, function calling, so accessing external tools, for example, structured outputs, and output guardrails. These can be challenging to implement yourself, so many companies turn to API providers. However, this means you'll be restricted to their functionality. You might not be able to fine-tune or access log probabilities, for example. Typically, proprietary models are easy to start with and scale, but they can become expensive with heavy usage and offer less flexibility. It's wise to design your application with a standard internal API so you can easily swap between models if needed. Control is another consideration. What happens if your API provider goes out of business, changes their terms of service, or is banned in certain regions? And if you want to run a model on device, third-party APIs aren't an option. There are numerous benchmarks for different use cases, and a tool that helps you evaluate a model on multiple benchmarks is called an evaluation harness. For example, OpenAI's evals lets you run any of around 500 existing benchmarks to evaluate their models. When using public leaderboards, you need to consider which benchmarks to include in your aggregated ranking, how to weigh different benchmarks, and how to handle benchmarks that use different metrics like accuracy, F1, BLEU, etc. Keep in mind that the goal is to select a small subset of models for more rigorous testing with your own benchmarks and metrics. Public benchmarks rarely represent your application's needs perfectly, and they may suffer from data contamination, which is when the models were trained on the same data they're being evaluated on. To deal with contamination, you first need to detect it using heuristics like n-gram overlapping and perplexity. If perplexity on the evaluation data is unusually low, it's possible the model has seen this during training. Once you've narrowed down your model candidates, you need a robust evaluation pipeline. Evaluate both the end-to-end output and each component's intermediate outputs independently. You can use something called turn-based evaluation, where you assess the quality of each output, and task-based evaluation, where you measure whether the system completes a task and how many turns it takes. First, think about what makes a good response, factors like relevance, factual consistency, and safety. Then create test queries and generate multiple responses to see how models perform. Develop detailed rubrics with examples for your scoring system. Whether you use binary scores, continuous scales, or something else depends on your data and your needs. The key is to make your rubric unambiguous so that human evaluators can follow it consistently.
Okay, we're stopping here because I need to pick up the kids. So this is being slower than expected. We've watched 21 minutes, but I don't know. I need to stop quite frequently because it's really interesting. The effort she has made to create this summary, I think is awesome. What I feel is that sometimes there are certain concepts that you actually need to go to the book for sure, because otherwise with this summary it's not being enough. But we'll go on in another session probably. So thank you very much.